Welcome to our video.
Hello, welcome to Chili's. Hi, welcome to Chili's.
Okay, exponential growth functions, okay? We're going to talk about exponential growth functions. We just got done in the last couple of chapters talking about exponential functions and talking about functions that are exponential with like a half up there or 2/3 up there or any, right, those type of things as well, okay? And that's because it's all leading up to us graphing exponential functions. And exponential functions has the form of this. Okay, y equals a times b to the x power. A cannot equal 0. Okay, and the base b is a positive number other than 1. So if a is greater than 0 and b is greater than 1, then the function y equals a times b to the x is an exponential growth function. Okay, it's exponential growth when a is greater than 0 and b is greater than 1. Because we're going to talk about decay, and it has different rules, like of what a and b have to equal. Okay, so if a is greater than 0, b is greater than 1, I have growth happening. Okay? B is the growth factor. You need to be able to identify growth factors, especially when you go into Mr. Rice's classes next year. He's going to ask you, at what growth factor does this take place? You got to look at the equation and say, that's the growth factor. The b is my growth factor. The simplest form of this equation, or the parent function of this equation, is y equals b to the x power. Okay, b to the x power. Where b is greater than 1, that's the parent function for the family of exponential growth. B being the base. The general shape of the graph is like this. Okay, it comes here. It goes through 0, 1. 1b, and it's growing like that, and it's coming here like this. The x-axis is the asymptote. We are going to start talking about asymptotes. An asymptote is like my cutoff point. It's never going to cross there. It's just going to ride that line out. It will continually get smaller and smaller and smaller, but by like decimal points, it's going to get smaller and smaller and smaller. It will never cross that. So an asymptote is where it's not going to cross. So on the parent function, my asymptote is the x-axis. Okay, it's a line that the graph approaches more and more closely, but never crosses. This graph rises from the left to the right. Okay, the domain of this parent function is all real numbers, because I can plug anything into x as long as it's a real number, because it's an exponent. Okay, so I can plug any number in, even negative exponents. They just have to be real numbers. I can't have imaginary numbers, which means I can't have radicals in there, basically, you know. Okay? And the range is y is greater than 0, because it's never going to cross the x-axis. I'm not going to have negative outputs. Okay? On this graph, on the basic parent function. What we're going to do today is we're going to start graphing some of these, and then we're going to look at some equations, exponential function equations that apply to real life things like taking out loans and stuff like that. Okay? What?
But oh goodness.
Oh goodness, I know. Being an adult. True, you actually might have used some of the formulas we're going to talk about. Okay? So, from there, we're going to practice graphing several of these today. I have 8 slides. Most of them are graphs. Okay? I want to graph y equals 2 to the x. Okay? So what I'm going to do when I graph y equals 2 to the x is, for exponential graphs, I'm literally just going to plug and chug. Okay? I'm going to plug numbers in, and I'm going to get outputs. Okay? So when I plug numbers in, I'm going to get outputs. I'm going to plug negatives and positives in, because I can plug negatives into my exponent. That's not a problem. So I'm going to just do -2, -1, 0, 1, 2. Make it easy. Okay? -2, -1, 0, 1, 2. Okay. negative 2 into this, what happens to that function? If it says 2 to the negative 2, it goes over 1. So I get 1 over 2 squared, which is 1/4. Okay, when I plug this in, this is what happens. You can't have a negative exponent, so you flip it, right? Which gives you 1/4. Don't forget to flip. The rules of exponents still apply. Okay? What happens when I plug a negative 1 in then? What is my output? 1/2. What happens when I plug 0 into an exponent?
0.
1. You always get 1. What happens when I plug 1 in?
2.
And what happens when I plug 2 in?
4.
So my graph is going to look like this. It's going to go negative 2, 1/4, negative 1, 1/2, 0, 1, 1, 2, and 2, 4. Right? I marked this one wrong, didn't I? He's like just making noises. Okay, so my graph is looking like this. Now, let's talk about this. The parent function went like this. It went here, right? And then it went 1b, whatever it is, blah, blah, blah. Because my parent function, well, no, that's fine. It's just working fine. That's a simple one. That's the simplest form you're going to get of this. Can you handle plugging numbers in, getting outputs, and graphing? Okay. What's my domain of this one? All real numbers. What's my range of this one? On this, it's y is greater than 0. Good. Nothing's changed to that. Okay. We're going to graph both of these on the same one. I'm just going to do them 2 different colors. Okay. So here we go. Okay, so this one right here, let's take a look at this function. When I have graphs like this, tell me what form this is in. If I wrote something like this, it's vertex form, good, it's vertex form. What does this A tell me? If it shrinks or stretches, and what else? What if it's negative? If it flips. What did the H and K tell me? The vertex, but it tells me what specifically does it do? It what? Yeah, it changes like all your points. It shifts all of my points left and right, up and down, right? Same rules are going to apply to when I'm graphing exponential functions. This right now is my A. Okay? What does my A do here? What's this graph going to change and do with that A being 1/2? It's going to shrink it. It's going to shrink it. Okay? So now I know that this graph should shrink at some point. Okay? So once again, you're just plugging numbers in. Okay? Plug numbers in. We're going to plug in -2, -1, 0, 1, 2. Okay. I plug these in. If I plug a -2 in, what happens to this? It flips to become what? 1/16, because 4 squared is 16. What's 1/16 times 1/2? 1/32. Okay. What is 4? If I plug -1 in, what do I get? Okay, what are you confused about? Okay. If I plug -1 in, I flip it and I get 1/4, right? What's 1/4 times 1/2? 1/8. What happens when I plug 0 in?
Wow.
What's 1 times 1/2? When I plug 1 in, what's 4 times 1/2? 2. And when I plug 2 in, I have 4 squared, which is 16. And then what's 16 times 1/2? 8. Now I can graph those points. 1, 2. I don't think I have enough room for 8. 2, 4, 6, 7, 8. We'll pretend like that's perfect. 0, 1/2. -1, 1/8, right? And -2, 1/6. So like I said, this is still, it's just never going to touch that line, but it is getting closer and closer to that line. Okay, what's my domain? What's my range? Okay, on these it is so far. Good. Over here, what's my graph going to do? Flip. It's gonna flip and it's gonna what? Nope. Because here's the deal. That's my B. My growth factor is 5 seconds. I have to have something like this in front of it to be my A. Okay? Don't get confused by that. I always do. Don't get confused by it. Okay? So once again, plug in numbers. Let's plug in -2, -1, 0, 1, 2. We'll just stick with our standard easiness. Okay. If I plug in a -2, what happens to that fraction?
What?
Look.
Maybe it is positive.
-5 seconds to the -2. What do? I flip this so that it says 2 squared over 5 squared, and I have this negative on the outside still. What's 2 squared?
4.
What's 5 squared?
25.
So I have 4 over 25, but I have that negative, so I have -4/25. Does that make sense, what I just did? Okay, rules of exponents. I distribute that exponent into both parts, and then I have to flip both parts because they're both negative. Okay? So you get -4/25, right? What happens when you plug in a -1? Flips, so I get 2/5, and then I have a negative on the outside, so I get -2/5. If I plug in a 0, what do you get?
1.
And then I get 1 times negative,
1.
so -1. What happens when I plug in a 1? Yeah, -5 seconds. And what happens if I plug in a 2? -25/4. Good. So then I graph all those. -2 and 4/25. -4/25. -2, -4/25. We're just gonna pretend like it's right there. -1, -2/5. 0, -1. 1, -5 seconds, which is 2.5, right? And then this should be -6 1/4.
Yes.
2, 4, 6, and 1/4, something like that. So this becomes like this. Now, talk to me about domain and range on this one. What's my domain? All real numbers. I can still plug anything up there. What's my range? Yes, y is less than 0 this time. Okay? Okay, now we get into more complicated ones, okay? Except for we're not going to make them complicated, we're going to make them easier. Okay, you remember how on your test I told you when you are doing square root and cube root functions, we want to focus on the easiest part and then we want to shift the points. We're going to do that on exponential functions as well. We're going to focus on this part here and then we're going to do the shifting with these, okay? Because I think that it makes it easier in the long run. There's less room for error. So we're going to take this function right here, and we're going to just look at this part, the 4 times 2 to the x. We're going to plug numbers in, and then from there, what are we going to do with -1 and -3? Okay, over which way one? No. It's negative, so it goes to the right. So I'm going to shift all my points right 1 and down 3 after I graph all these inputs and outputs. Does that make sense what I'm saying? Okay, so let's plug in again. -2, -1, 0, 1, 2. Literally, stick with easy numbers. Make your life easy. If I plug -2 in here, what does that do to 2 to the -2? It gives me 1/4, and then 1/4 times 4 is? Good. When I plug in -1, what does it give me? It gives me 1/2, and 1/2 times 4 is? Good. When I plug in 0, what does it give me? 1, so 4. And if I plug in 1, what does it give me? 2, and then 2 times 4 is 8. And then if I plug in 2, it's going to give me 16, okay? So I probably won't graph those because those are like way off my scale, but we get the visual. So -2, 1. -1, 2. 0, 4. 1, 8. 4, 5, 6, 7, 8. 7, 8. I'm gonna pretend that's right there, but I'm just gonna ignore this because it's a little out of my range. Now, that's the graph before I apply over 1, down 3, right? So I'm going to go over 1, and I'm going to go down 1, 2, 3. There's my point. I'm going to go over 1, and I'm going to go down 1, 2, 3. Over 1, 1, 2, 3. And then this one's like up here, and I'm going to go over 1, 1, 2, 3. Okay? And this becomes my graph of that function. Does that make sense? Okay, now, domain. What?
Do you have to graph the first one then?
Yes, I want you to graph the first and shift it from those points. All real numbers. Domain's all real numbers. Range. No. Where is my asymptote for my range?
Ah, -2.
Not -2. Listen, it's very easy. I'm going to give you a hint. You'll look at this. So my range always comes from there. So my range is y is greater than what?
-3.
-3. Because this one is facing up. If it was facing down, it would be y is less than -3. So my asymptote and my range always come from this number right here. That's how I can tell. That simple. Okay? Does that make sense? Okay. So then, that's like one of the most complicated ones we're going to graph. Now we're going to talk about formulas. These two formulas I'm going to give you, you have to memorize. Mr. Rice says, period, memorize, because when you get to him, you need to know them. Okay? Exponential growth model, which you should have done this in 8th grade. I know you did because I taught it last week to my 8th graders. Okay? That when you're doing exponential growth, the standard formula for it, when it's increasing by a fixed percent, okay, by a fixed percent each year or other time period, the amount of y is the quantity after t years can be modeled by y equals a times 1 plus r to the t. This r is your percent increase or your rate, okay? Your percent increase or your rate. Your A, right here, is the initial amount, the amount you start with, okay? This whole section here, this 1 plus R, is known as your growth factor. You need to know that that is your growth factor.
So it's like the B.
Yes, exactly. It is your B. Yes. You need to be able to know that and compare those two things. It's your growth factor. Good. And then the T is like the time in years, okay? So it's y equals A times 1 plus R to the T. Now, we're not going to graph this because it's going to be impossible for us to graph it without a graphing calculator, but we're going to come up with a formula for it because we can do that. In 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% each year. Yeah. Write an exponential growth model giving the number n of incidents t years after 1996. About how many incidents were there in 2003? So we'll talk about that in a minute. How can I write a formula for this?
2,573.
Okay. Y equals 2,573 because he's saying that's our initial starting place. Okay. And then what? Yep.
Times 1 plus 92%.
How do you turn 92%? Remember, 92% always has to be a decimal.
0.92.
0.92. So I'm
This is
going
on the ACT.
It is on the ACT.
I just did problem 1.
0.92. And then it's to the T, right? Because right now they just want the formula, which means my T should not be filled in. Okay? Now, if I wanted to figure out in 2003, how many years is it from 1996 to 2003? How many years is it from 1996 to 2003?
Seven. No?
She's probably gonna say she
Is
was.
that wrong?
No, you're right. Seven. So if I want to solve this for 2003, right, I would say y equals 2,573 times 1.92 to the 7, yes? What does that come out to be? This is why you have to have calculators on your homework.
96.2.
996.2.
No. 96.1852772.
No,
Did I do it wrong? I probably did.
yes.
I got a very large number.
200,
47,487.71.
yep. It should be around 247,485,
I think my
something like that. 247,485. Should be congruent to that, okay?
Oh, you meant the whole thing?
What?
I just did the 19.
Oh, you just did 1.92 to the 7? Yeah, you still have to multiply by the initial, okay? So that's about how many viruses there were 7 years later. That's what it's saying. If it continues to increase by 92% a year, that's what it would look like. Okay, so now it would be like insane amount, right? Since 1796. Okay, the other one we need to talk about is compound interest. This is very important when you as an adult are taking out loans. Okay? When you take out student loans, when you take out a home loan, a car loan, you don't want compound interest if you can stay away from it. You probably can't, which means your rate needs to be low. So with compound interest, the difference between this and the interest we just talked about is if I take out something, a loan, and let's say it's going to have compound interest monthly, okay, and I'm paying 3% on $1,000, that means after 1 month, I pay 3% towards that, I gain 3% in what I owe of that $1,000. Well, after month 2, I gain 3% of what was there from month 1. After month 3, I'm paying 3% more on what was there after month 1 and 2 combined. So I'm going to keep growing off of the interest that I'm already paying, which makes it harder to pay your bills off quicker, right? Because your interest rate is just killing you. So if all you can do is pay your interest, you're never going to pay your bill off. You need to be able to make payments that are larger than what your minimum payment is supposed to be, which is going to suck. Or else you're going to pay loans for, like, when you take student loans out, usually they don't start the loan until after you graduate or stop going to school. Some loans start day 1 when you take them out. So, like, as your freshman year, if you take them out, they're going to continue to build interest on them through your senior year, okay? Those are rough. When you take out student loans, a lot of times also, you're going to take out loans that are, some of my friends had like $60,000 in loans, like just individually by themselves, not including their husband or wife or whatever, okay? They have them set up to pay the minimum payment of like $400, let's say, a month for 30 years or 20 years. So for 20 years, they're paying $400 a month towards their student loans from college. That's stupid. Like, that's just dumb to be paying for 20 years, just yours, $400, plus whatever your husband's is, another $200, you know what I'm saying, or your wife's. When I took loans out, I think I took out loans for like $10,400 over 4 years of college, and I paid it all off in 1 year. So you need to make sure that when you go to decide to go to school, be smart about how much money you're taking loans out wise, because you have to pay them back, not your parents. And you don't want to be paying a house payment or an apartment payment on loans each month and not afford to live someplace that you want to live. Does that make sense? It'd be better to have a nice apartment or a nice house than to pay $600 a month on your student loans. Just a thought. So, sometimes it's better to go to a place that we're not quite as excited about, but I can get the same education and it not cost me in the long run. There are some degrees where it is important with the name behind it, right? If I go to Yale Law School, that's gonna get me a good job. Okay, and Yale's super expensive a year, like 60,000 or more, I think, okay? But that might be worth it in the long run, cause you're gonna make a lot of money being a lawyer that got hired from Yale, right? But if I'm going to Yale and I'm going to be a teacher, and I am supposed to pay that up front, and I'm not getting any scholarships or anything, that's stupid, because my teaching salary is not going to match what I'm taking out in loans, right? So be smart about those decisions. So compound interest is A equals P times 1 plus R over N to the NT. The only thing that changes in this formula is P stands for your principal. The N is the times per year. So they might say quarterly, they might say monthly, they might say daily. That's what goes there. So if you have common sense and you know how many months are in a year, you can fill that in. Okay? So then the last slide is just a practice problem on this. It says you deposit $4,000 in an account that pays 2.92% annual interest. Find the balance after 1 year if the interest is compounded within the given frequency. So first we're gonna do it quarterly. How would I set that up? A equals what? What's my initial? 4,000. And then the formula says 1 plus what? Rate over N. Rate over N. 2.92, how do I change that into a decimal? Because that's a percent right now.
0.29.
Not 0.29. Your decimal has to, yeah, 0.029. So 2% is 0.0292 over, it says quarterly, so 4. And then to the NT, so 4 times, and it says 1 year, so just 4 times 1, right? Okay, so when I do this, I get 4,000, and I don't know what 0.0292 over 4 is, but I'm going to figure out. So you're gonna get this to the 4th, right? So what does that come out to equal? What is 4,000 times 1.0073 to the 4th? Okay, $4,118 and like 8 cents, 8 or 9 cents. Yours might be a little off from the book because your calculator's not as advanced as mine, so it's not gonna round as perfectly. Now, that's after if it was quarterly. Let's look at what it would be if it was daily, okay? Daily, the only thing that changes is my what? Your N. So, instead of saying over 4, I'm gonna say over how much? If it's daily, in a year. 365. We're just gonna go with the standard 365. Okay. So let's figure out, what does that come out to equal?
12.
I don't think your answer's right then.
I got
It
it.
says 1 over 12,500.
Oh, you mean right here?
Yeah.
Oh, I wouldn't, if I'm you, I wouldn't do that. I would just go and plug in my calculator, 4,000 parentheses 1 plus, that has to be in a double set of parentheses, because it's not gonna, yeah, you're not gonna. Plus 1.0292 divided by 365, and then to the 365, what do you get as your answer? Perfect. So you get this, 4,118.52. Now, right now, let's talk about this. Right now, this doesn't look like much of a difference, does it? Okay? After 1 year, that's at 0.8 cents, this is at 0.52 cents. But think about this, after 20 years, okay, that would be a big difference, because this would be compounding daily for 20 years. This would be compounding once or 4 times a year for 20 years. So it's going to make a larger difference the longer you keep your money in that bank or that you keep your money invested. So that's why in econ and stuff, they always talk about writing out your investment, right? Because the stock changes and all that. If you can write it out, you're gonna make a longer, you're gonna make more money in the long run, if I could talk.